Welcome students. Today we are going to study about the concept called to be continuous charge distribution. What do you mean by that continuous charge distribution? In our last class we have studied about the concept called to be electrical field at a point. Okay, we have studied electrical field at a point due to a point charge. So when you are considering the electrical field at a point due to a point charge, the formula that you can able to get is E vector is equal to 1 divided by 4 pi epsilon 0 Q1 into Q2 divided by R square into R cap divided by that point charge Q2. So Q2 or Q0 will get cancelled and the net electrical field that we are getting is E vector is equal to 1 divided by 4 pi epsilon 0 into, instead of Q1 I am writing it as Q divided by R square into R cap. This formula holds good. This formula holds good only for what? Only for discrete or point charges. Discrete, or we can say it out as point charges. See, then what we are going to study today, instead of the charges considered to be a point charge or an discrete charge, if you are having the charge is a charged sphere or a charged wire or a charged surface area, what we can able to do? That is what we are stating it as continuous charge distribution. So what we are going to do, if you are dealing with, if we are dealing with a charged sphere, if you are dealing with a charged sphere, or if we are dealing with a linear conductor having charge, linear conductor, that is a long conductor having charge, a long conductor having charge, or an plane area, or a plane area which is said to be charged. See, in these cases, if you are considering or if you are dealing with a charged sphere or a charged linear conductor or a charged plane area, then we cannot apply the previous method. Then in this case, it is very difficult to see the individual charges. See, in all these cases, it is very difficult. It is very difficult to see or to look at individual charges. To look at individual charges. So what we have to do? To look at individual charges. Then what we can do? In that case, we have to assume that the charges are continuously distributed and discrete charges are not considered. So in these cases, we have to consider that, in these cases, we should consider that the charges are continuously distributed and discrete charges are not considered, and discrete are separate, whatever may be, usually discrete. So discrete charges are not considered. Charges are not considered. This is what we are going to study here. See, look at again. If you are considering the charges as an individual charge, then the individual charge can able to get the electrical field at a point using this formula, that E vector is equal to 1 by 4 pi epsilon 0 q by r square into r cap. I have written it here. This holds good only for the discrete or the point charges. But at the same time, if we are dealing with a charged sphere, see like this, you are having a sphere which is said to be charged, which is having a positive charge. Or if you are having a long conductor, and if this long conductor is said to be positively charged, or you can say you are having a plane area, a surface area in which the charges are said to be uniformly distributed. In these cases, that is what I have written here. If we are dealing with a charged sphere or a linear conductor or a charged plane area, then it is very difficult for us to look at the individual or the discrete charges. So in that case, what we have to consider? In that case, we should consider that the charges are, okay, in this case we have to consider the charges are continuously distributed either in the sphere or in the linear conductor or in the plane area. And in these cases, individual charges are not considered. We have to take the charges are distributed in that objects continuously. So how we can able to attain the formula? Let us go through that formula, how we can able to derive. Initially, we are going to derive it in general, and then we will be stating 3 cases in order to determine the electrical field due to a sphere, due to a linear conductor, and due to a plane surface area. So we are going to study about in general, and that is the electrical field due to continuous charge distribution. In your book, it is the point number or topic number 1.33, and the topic that we are going to study here is electric field due to continuous electrical field due to continuous charge distribution. Continuous charge distribution. What we have studied previously is an introduction, and here, right from here, we are going to derive an expression. Let us see. So, in order to derive an expression, what I am doing is, I am considering an irregularly shaped rigid body. If I am considering this irregularly rigid body, I am taking that this body is completely charged. What type of charge is given? The charged or the charge that was being given to this body is taken to be positive. The charges here are distributed continuously inside this. So the entire object which is having this charge, let us consider like this. At this point, you are having a charge, a small amount of charge, considered to be delta Q1. Here I am having another charge. I am taking it as delta Q2. Here I am considering another charge, taking it as delta Q3. Like this, it is having indefinite or infinite number of charges in it. Now, due to the distribution of charges in this irregularly shaped object, what is the electrical field? Because if your charge is present around that charge, you will be having the electrical field. Now, you are not having a discrete charge. You are having so many charges distributed here. Due to all these charges, what is the electrical field at this position? Let us take that point as P. What is the total electrical field or net electrical field available at this point? I have to calculate this E vector. How to calculate? For that, I have to calculate initially the electrical field at this point P due to individual charges. Due to Q1, if you are considering the distance, let it be R1. If you are considering from Q2, the distance of this point is taken to be R2. If you are considering from Q3, let us consider it as R3. So, due to Q1, the electrical field will be acting away from that positive charge and let it be E1. Due to this Q2, it is also acting away and let us write it out as E2. Then let us consider this Q3. Due to Q3, it is acting away. If it is acting away, let it be E3. Then we have studied in superposition principle. By using that superposition principle, taking the vector sum of all these three vectors, we can able to calculate the net electrical field. That is the concept we are going to deal with. So, first of all, let us consider or let us write the description of this diagram. And small introduction again. Description for this diagram again. What is the description? First of all, you consider an irregularly charged object. Consider an irregular charged object. Okay, the first point. Then the entire object is divided into large number of charge element. The second point is, this is point number 1 and point number 2. See, the entire object is divided into large number of charged elements. Large number of charged elements. What is that large number of charged elements? That is, one of the charged element is delta Q1, second charged element delta Q2, third charged element delta Q3. Like this, it is going on till delta Qn. Okay, and each charge element is taken to be positive charge, and let us consider each element is positively charged. Now let us go for the next one. What is that next one? See, the electrical field at that point we have to calculate due to all these charges. So according to superposition principle, according to the superposition principle, the total or the net electrical field, the net electric field at what? The net electrical field at P is, what is that net electrical field at P? P is this position at this point. Due to all the continuously distributed charges, the net electrical field E vector is equal to E1 vector plus E2 vector plus E3 vector plus E4 vector plus etc. up to what? Up to En vector. Now we have to calculate what is that values. That is, what is E1, what is E2, what is E3, what is E4, etc. But what it is given in your book is, for delta Q1, the electrical field is given as delta E1. For delta Q2, the electrical field is given as delta E2. Same da. Then instead of delta Q3, I can write it out as delta E3. Here I can write it out as delta E4. Then I can write it here as delta En. Like this it is going on. Now what I have to consider? What I have to consider is, now I have to calculate what is the formula for or value for delta E1, what is the value for delta E2, what is the value for delta E3, etc. And then I have to take a vector sum. So therefore, first of all, I am writing what is the value of delta E1. Delta E1 is 1 by 4 pi epsilon 0. Instead of Q, you are getting delta Q1 divided by, what is the distance of Q1 from P? It is R1. So R1 square multiplied it with R1 cap. Similarly, delta E2. What is delta E2? Again, 1 by 4 pi epsilon 0 delta Q2 divided by R2 square R2 cap. Go for delta E3. Delta E3, all are considered to be vectors because R1 cap, here you have written it as R2 cap. And now delta E3 vector equal to 1 by 4 pi epsilon 0 into delta Q3 divided by R3 square into R3 cap, and so on. If it is going on like this, finally I can write the value for delta En cap. What is that value? Delta En cap then 1 by 4 pi epsilon 0 delta Qn by Rn square into Rn cap. Clear? Now I have individually written what it is given for each and every basic quantity. Now the net electrical field. So I can able to calculate net electrical field at the point P, which is equal to E vector equal to what we have written, delta E1. What is delta E1? Delta E1 is 1 by 4 pi epsilon 0 delta Q1 divided by R1 square into R1 cap plus second one, delta E2. What is delta E2? Here I have written, you see, 1 by 4 pi epsilon 0 delta Q2 divided by R3 square R3 cap plus, like this it is going on. It is not necessary to write each and every term. I can simplify this. How? See, the net electrical field E vector is equal to 1 by 4 pi epsilon 0 is available in each and every term. So I am taking it as an common factor, 1 by 4 pi epsilon 0 into remaining delta Q1 divided by R1 square into R1 cap plus second term delta Q2 divided by R2 square into R2 cap. If it is going on for the remaining terms, finally I can write delta Qn divided by R3 square into Rn, sorry, not R3, it is Rn. So Rn square into Rn cap. Now, since I have taken it as delta Q1 by R1 square into R1 cap, or delta Q into R3 cap like this, since I have written, I can consider what? I can take like this. What I can take like this? I can write all these in an mathematical form using summation. So in mathematics, or I can write mathematically, okay, mathematically I can write it out as E vector is equal to, see, 1 by 4 pi epsilon 0 into. Now you see, these terms can be written in words of sigma. Sigma of, instead of delta Q1, I can write delta Qi by, instead of R1, I can write Ri square, and instead of R1 cap, I can write Ri cap. Then what is this I? This I will range from 1 to n. So this summation will be giving you the positive signature or the positive sign. Let us take this as equation number 1. This equation gives you the net electrical field at the point P due to the irregularly shaped object. See, this equation denotes or gives the net electrical field at the point P due to the irregularly shaped object. See, but this equation is approximate. This equation is not so accurate. This equation is considered to be an approximate value. Using this, what we can do? We can write this summation in terms of integral. How I can consider it in terms of integration? See, in integral value you might have studied delta Q tends to 0 like that. So, to incorporate the continuous distribution, what I can do? To incorporate the continuous distribution, see, what I can take is, we can apply a limit. We apply limit in such a way that if delta Q tends to 0, then this delta Q can be written as dq. A small charge, nothing but a small charge or infinitesimally small charge, nothing but a very small charge. In this case, therefore, the summation of the above equation can be written as, or we can write the above equation can be written as, removing the summation, I can state as E vector is equal to 1 by 4 pi epsilon 0. Instead of this summation, I am putting an integral value. If I am putting an integral value, then I have to apply the limit that delta Q tends to 0. Automatically this delta Q will become dq divided by, then the concept is r square multiplied with r cap. This is what we can state it out as the equation for the continuous distribution. See, moreover, in this case, I have written r. What is this r? R is taken to be the distance of P from the small r infinitesimal charge dq. That from the small charge dq, the point P is at a distance of r. The point P is at a distance of r. If you are writing it as r cap is the unit vector. R cap is the unit vector from the charge, small infinitesimal charge dq to the point P. Clear? So this we are considering it as what? This we are considering it as the continuous distribution of a general equation for the electrical field due to continuous distribution of charges. Using this, we have to go for 3 special cases. What are the 3 special cases? You see, we can consider different objects which are said to be charged. We are going to consider regularly shaped bodies, one as a spherical body, another one as a linear conductor, and another one as a plane surface. In that case, what is the net electrical field? That we will see it in our next video. This is the general equation, and the special cases we will study in our next video.